All right, hey there guys. For this lesson, we're going to be talking about basic antiderivatives, which is the process of finding those integrals, right? We've seen the integral symbol, but we're going to learn how to do it by hand. So we had a process for finding derivatives, and now we're going to talk about doing the same thing for antiderivatives. The most helpful thing I can tell you with this is that antiderivatives are undoing what a derivative did. So think about those derivative rules that you know. Today we're starting just with our basic power rule, and we're going to talk about some trig functions as well to get you prepared for the quiz that goes along with this lesson. So let's jump right in. First thing I want to share is that I have uploaded what I'm calling a calculus cheat sheet, and I wish I would have done this last semester. You definitely could have used it. It's got some great information. So it's 11 pages long. Don't let that stress you out. Really, like the first probably 6 pages are the most useful. And I think you'll find what is useful and what is not, but take some time to look over it, highlight the really important things. And if you want to go through it together, just reach out to me and I'd be happy to kind of show you where you can be highlighting and what to really focus on. But I've taken a snip here of the common integrals that comes from the cheat sheet. I believe this was right around page 5 or 6 that you'll find this. And this is what we want to really be focusing on as we're learning those basic antiderivatives. So I want to focus first on this power rule here. This is undoing the power rule for deriving. So if you're going to find the antiderivative of a power function, you're going to add 1 to the exponent, because remember with deriving we subtracted, and then you're going to divide by the new exponent. So you are literally just undoing what you did with the derivative. So again, we add 1 to the exponent and then you divide by that new exponent. Okay. I don't know if the lesson goes over this yet, but if you have an x to the negative 1, then that is the same as having 1 over x, and that is actually a different antiderivative, that is the natural log. So again, knowing these common integrals is what's going to be important for a lesson like this. Okay, focusing here on the power rule, and then we're going to talk a lot about trig. So focus a lot on the trig ones. Have your cheat sheet out so that we can go through those examples together. Okay, so example 1 here, you can see that we're looking at some powers. We've got a power function here, and so just like we learned last week, you can separate addition and subtraction to find these integrals individually. So starting with 8x to the third here, I'm going to add 1 to the exponent, which is going to give me 8x to the fourth, and then I divide by that new power. So I'm dividing that term by 4. Moving on to the next one here, I have 9x squared, so I'm going to add 1 to the exponent there, which is going to give me 9x to the third, and then I'm going to divide by that new power, so I'm dividing by 3. On this last one here, I have a constant, so thinking about what would have happened, how we derive to get to a constant, we have to go ahead and put an x to that. So this is like having an x to the 0. If I'm going to add an exponent, then I'm going to end up with a 4x to the first power, which is just 4x. Every antiderivative, and you'll see it on your cheat sheet as well, always has this plus c. And that's because, think about when you're deriving, you can have any constant at the end of a derivative and it's always going to go out to 0. And so if you have an antiderivative, you have to remember that there could be any number at the end of that antiderivative that would still be the correct antiderivative for that function. From here, we would just simplify this. So 8 over 4 reduces to 2x to the fourth, 9 over 3 reduces to 3x to the third, and then we have plus 4x plus c. And that right there is the antiderivative of that function. Let's go ahead and take a look at example 2. This one is not quite as obvious, but this is still a power type function. So we're going to start by rewriting this with power. So the square root of x, if you recall, is the same thing as having x to the 1/2. And then here we have 1 over 2 square root of x. Well, since that x is in the denominator, we want to move it up and give it a negative exponent. So this is 1/2 x to the negative 1/2. Okay, so that's just rewriting it so that it's in a power so that we can then apply the power rule. So now I'm going to do the same thing I did in example 1. In this first term here, I start by adding 1. Remember that you're adding a whole to a fraction, so I'm really adding 2 over 2, right? That common denominator to our fraction. So that gives me x to the 3/2, and then I divide by that new power, so divide by 3 over 2. This is going to look really ugly at first, but we'll get it looking better. Here I do the same thing, so I'm adding a positive 2 over 2. So that's going to give me 1/2 x to the positive 1/2 when I add those together, and then I divide by that new power, so I divide by 1/2. And don't forget there's always a plus c when we do an antiderivative. I will tell you on the AP test that plus c will get you. You'll lose points if you don't put a plus c on a free response, so just keep that in mind. So now at this point, I need to do some simplifying. Because I'm dividing by a fraction, that means I'm going to multiply by the reciprocal. So this becomes 2/3 x to the 3/2. This one here, I have 1/2 x to the 1/2, and I'm multiplying by 2 over 1 because I have to multiply by the reciprocal of the denominator. And so you can see when I multiply these together, the 1/2 and the 2 are going to cancel out, which is just going to leave me with a final function of 2/3 x to the 3/2 plus x to the 1/2 plus c. And that right there is the antiderivative for this function. Moving on to example 3, again, we have a power looking function, but this one is a little bit different. So one of the things I want to really stress is if it's not just a very basic polynomial, then look for simplifying, look for ways to simplify. So it is important to think about how we can simplify a function. In this case here, this can be simplified by distributing that x to the 4th and then using some exponent rules. So this would be x squared over x to the 4th plus 2x over x to the 4th minus 3 over x to the 4th. Okay, so again, just rewriting it. Now, we haven't learned anything with fractions, so again, we have to do some rewriting so that this looks like a polynomial. We just want terms with exponents, no division going on or anything like that. So remember that when you have exponents that are being divided, you can subtract them. And so this is going to give me x to the -2 plus 2x to the -3, because I subtracted 1 minus 4. Minus 3x to the -4, because that exponent in the denominator can be moved to the top, and then we just make it a negative. Now this is ready to apply the power rule because I have just single terms, exponents and variables in the numerator, no division happening. So I'm going to follow that rule we've been talking about. So I add 1 to the exponent, so that's x to the -1, and I divide by that new exponent, divide by -1. Next term, I add 1 to the exponent, so I have 2x to the -2, and then I divide by that new exponent, so I'm dividing by -2. Last term here, I add 1 to the exponent, so I get minus 3x to the -3, and I divide by that new exponent, which is -3. Don't forget your plus c at the very end, and then we're going to do some simplifying here. So this first term, we're just dividing by a -1, so this becomes -x to the -1. Here we have 2 divided by -2, so this becomes minus x to the -2. And here we have -3 divided by -3, so that becomes a positive x to the -3 plus c. I'm perfectly fine with a final answer like this, but know that you can also write those negative exponents. You can simplify them by moving them to the bottom. So we end up with -1 over x minus 1 over x squared plus 1 over x to the 3rd. So all I did was I took those negative exponents and I moved them to the bottom to make them a positive. So either one of these answers would be acceptable to me. Make sure that you're paying attention to the instructions in the quiz or anything like that if you encounter a question like this. Example 4, here's where we get to talking about trig. So bust out that trig knowledge that you have. That's super important. You're going to need to know your trig identities. If you're struggling with those, please reach out to me. I'm happy to put together some things that can help you and just kind of a refresher for you. And we can definitely talk in more detail if you need that. So looking here, first thing I need to do if I see multiplication like this, I want to go ahead and start simplifying by distributing this. So I'm going to have the integral of secant of y tangent of y minus secant squared of y. okay, dy. I do want to point out the variable doesn't matter. We've just changed the variable that our function is in, and so with that y, we're also changing what we're integrating in terms of, which is that dy at the end. Okay, so that's only changing because the variable has changed. Now, in the first term here, secant y tangent of y, you can use your cheat sheet, but you're going to find that there is nothing here. There's nothing for integrating secant of y tangent of y. So what we want to do is use our trig functions to, or our trig identities, I'm sorry, to simplify this or rewrite this. So remember that secant is the reciprocal of cosine. So we have 1 over cosine of y. Oh, I take this back. You are likely going to find this on your cheat sheet. So let's go back to that cheat sheet and see if we can find secant of a variable, tangent of a variable. And we see that that's right here. So I found the antiderivative of secant of u, tangent of u is equal to secant of u. So that means, what this means here is if you derive secant of u, then you get secant u tangent u. So then if you're integrating, you're anti-deriving secant of u, tangent of u, you get secant of u. Okay, so again, knowing that relationship between derivatives and antiderivatives is important. So now that we've distributed, we've got a common, if that's what you want to call it, antiderivative here of secant of y, tangent of y, which we know is just secant of y. And then this one here, secant squared of y, hopefully this one you recognize because we did use this derivative a little more often. And so this one here becomes tangent of y, because when you derive tangent, you get secant squared. Don't forget that there's still that plus c at the end, so we're always putting a plus c at the end of our antiderivative. I want to go through one last example, which is a little more challenging, I guess, and how to work through this. And this is, I really just want to emphasize the goal is to simplify. We're trying to simplify these things to get to a point where we can actually work with them. So division like this, we cannot simplify with division. As I look at this, there's not really anything I can do to cancel out or anything like that. So there's a very important identity here that we need to be able to recognize. I don't believe it's on your cheat sheet, but you'll want to maybe add it, okay? So the identity is cosine squared of x plus sine squared of x is equal to 1. This is called a Pythagorean identity. You would have learned it in a pre-cal type class or a trig class. And we use this identity often. So that's exactly what's going to happen here is we see that 1 minus sine squared x, if I just manipulate this equation here and I subtract sine squared of x from this side, then I know that 1 minus sine squared x is equal to cosine squared of x. So that's exactly how I'm going to rewrite this. I'm going to write this as sine of x over cosine squared of x. Now, this still may not look very obvious. We still have fractions. We have nothing to simplify yet. But if we break this down even farther, we can break apart this cosine of x. And when I break that apart, then I end up with sine of x over cosine of x times 1 over cosine of x. Right? So all I did was split up cosine squared x into each of those things there. Sine goes over one of them, and then I just have a 1 left over. Now sine of x over cosine of x, again, thinking about those trig identities and what we know about that, is equal to tangent of x. And 1 over cosine of x, that reciprocal identity, is secant of x. So this is the one that we just encountered on the last example. I was thinking it was something else, which is why I didn't prep you to get your cheat sheet ready. But since we've already talked about it, that makes it easier to do this antiderivative, because now we know that the antiderivative of tangent of x secant of x is equal to secant of x. And then don't forget that plus c at the end. So again, the big goal here is to simplify the equation that's on the inside so that you're dealing with something simple, and then go ahead and apply those antiderivative properties that we talked about. Use your cheat sheet, get comfortable with that. If you need more practice, here's the pages and the numbers to try. I use the odd numbers only because the answers are in the back of the textbook, so you can always check your work. If you're having trouble, please reach out. And otherwise, I'll see you guys on Friday.